Okay, welcome back, students. Let's cover 3.1 to 3.4 today, or actually 3.1 to 3.2 in this session. Okay, the objectives are going to be to define and calculate basic probabilities using relative frequency, define the complement of an event and its probability, and use probability to determine if an event is unusual. So that's what we'll be covering in this video. Okay, random. An event is truly random if each outcome has an equal chance of occurring. Okay, probability, informal definition. The chances or likelihood that an event will occur. Okay, a little more formal is the probability is the predicted long-run relative frequency of an event, meaning that if we did something many times over, the probability of an event is the proportion of times that we saw the event actually occur. Proportion just meaning the fraction, okay? Okay, so I'll put fraction here. It's the fraction amount of times we saw the event occur, okay? So, like flipping a coin, okay, the number of times it lands on heads is a possible outcome, okay? So the event is an outcome or collection set of events. Example, rolling a die, rolling 1, 2, 3, 4, 5, or 6 are all outcomes. But rolling an odd, 1, 3, or 5 is an event. Okay, so it's the event out of all the outcomes. The sample space is the total set of all possible outcomes. So what's the sample space for flipping a coin? Okay, would be heads and tails. So there's two possible results. That's the sample space. That's all the possible outcomes for flipping a coin. Okay. If every outcome has an equal chance of occurring, we can just use counting to calculate. The probability of event A can be written as the number of outcomes in A, okay, or what we want to have happen over the total number of possible outcomes. So this is called the desired outcomes. Oops, sorry. Over the possible outcomes. Okay, suppose we roll a 6-sided die. List out the sample space. So this is all the possible results. So I could roll a 1, a 2, a 3, a 4, a 5, or a 6. Okay, what's the probability of rolling a 1? Well, what's the desired result? Well, there's one desired result, that's rolling a 1 out of 6 total results. So that would be 1/6. What's the probability of rolling an odd? Well, what's the event? The event is 1, 3, or 5 out of the total sample. So there's 3 desired outcomes over the sample space of 6, over 6 total outcomes. So that would be 3/6, or it would reduce to 1/2. What's the probability of rolling a number less than 5? Well, again, what's my event space? It's 1, 2, 3, or 4. Okay, so those are the desired outcomes, okay, over the total outcomes. So there's 4 out of 6 total outcomes, okay? So what's the total outcomes? It would be just my sample space. To all the possible outcomes would be 3, 4, 5, 6. And so we just add the number up. We say, okay, there's 4 on the top that I could get that I want out of 6 on the bottom that I could just get, whether or not I want them or not. Okay. And that would reduce to 2/3 by dividing both top and bottom by 2. Okay, probability of rolling a number greater than 6. Well, there are no numbers greater than 6. So we just say that there's 0 out of 6, or that there's what's called a null space. There's nothing there. Okay, this equals 0. Okay, and we say that that's not possible. Suppose there are 300 people sitting in a theater. 210 of them own an iPhone. If a person is chosen at random, what is the probability that the person chosen owns an iPhone? Well, it would be the desired amount of people out of the total amount of people. Okay, so this becomes 210 over 300. That will reduce to 7 over 10, which is 0.7 or 70%. Okay, probability distribution. Probability distribution is every possible outcome of a random event. Okay, and relative frequency in the long run for each outcome. Okay, so think whenever it says relative frequency, think percentage. Okay, percentage in the long run. So if you flipped a coin, what would be your long run probability? Well, 0.5 would be heads and 0.5 would be tails. Okay, so for flipping a coin, okay, 0.5 heads, long run probability, half of them would be heads and half of them would be tails. Okay, so in the long run. Okay, basic rules of probability. In any probability distribution, something has to happen. The sum of all the probabilities of the distribution must be equal to 1. Okay, so all the possibilities must be equal to 1. The probabilities must be positive. Okay, so let's look at the possible outcomes for rolling a die. Well, the possible outcomes we saw was getting a 1, a 2, a 3, a 4, a 5, or a 6. What's the probabilities? Well, it's 1 out of 6, 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 1 out of 6. This is the distribution for all possible outcomes. Okay, and would this add up to 1? Would all these probabilities add up to 1? Yes, they would. I would get 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, and that would be 6/6, which is 1. Okay, so the probabilities are all the same. In this case, they're all 1/6. And do they add up to 1? Yes. So all probabilities are the same. This again is the probability distribution. The probability distribution. Okay, there are 10 marbles in a bag. Okay, 5 blue, 3 red, 2 yellow. 1 marble is pulled out at random. Okay, the color is observed. What are the possible outcomes here? Well, the possible outcomes are the colors. We could have a blue, we could have a red, or we could have a yellow marble. Okay, what's the probability of getting a blue marble? Well, it's 5 out of 10. Okay, which is 1/2. What's the probability of getting a red marble? Well, it's just 3 out of 10. What's the probability of getting a blue? 2 out of 10, which is 1/5. Okay, and does this add up to 1? Well, we could add the fractions if we wanted. We could also change this to decimals if we wanted. 0.5, 0.3, and 0.2. And we could see that, yes, 0.5 plus 0.3 plus 0.2 will add up to 1.0, which is 1. Okay. So what's wrong in these examples? If I have blue as 0.525, red as 0.35, and yellow as negative 0.45, if I add these up, 0.25 plus 0.35 plus 0.45, let's do that on the calculator. Okay, so let's clear that. 0.25 plus 0.35 plus 0.45 we can see that we get 1.05. Okay. Okay, so which is not 1. Okay, so this does not equal 1, and so that's what's wrong here. Okay. Probabilities must sum to 1. Okay, it does not sum to 1. Probabilities must sum to 1. Okay, for a distribution. Okay, what's wrong here? Well, do these sum to 1? Yeah, they do. However, we have this guy here, which is a negative probability, and you cannot have negative probabilities. Cannot have negative probabilities. Oops, I think I spelled that wrong. Probabilities. There we go. It's better. Okay, complement. What does the complement mean? The complement of A, denoted AC or A with a bar over it, is the set of all outcomes not in A. Okay, and so we can actually say, well, instead of looking for what's not in A, we can look for what is in A and then subtract it from 1. Okay, that's what this formula says. We can just say, oh, it's 100%, right? So think of it like a pie chart, okay, and we had, say, 50% here, 25% here, and 25% here, right? We have to add up to 100%. Okay, and I want to say this is A, B, and C. Okay, so A, B, and C. I'm gonna put the C. Oops, I'll put the C above this. Okay, and so if I said not C, okay, not C, I want the probability of not getting C, then what could I do? I could say that that's 1 minus the probability of getting A and B. Okay, so we would say that not C is 1 minus, okay, oh, sorry, this is 1 minus C, the probability of C, sorry. We can either add up A and B, which is 0.5, or we can just go 1 minus the probability of C, which is 0.5, which equals 0.5. Okay. Okay. Maybe it would have been better if I just looked at A here. Let's just look at A. Okay, let's go. The probability of not A is 1 minus the probability of A. Okay, so what is that? Probability of not A is 1 minus the probability of A, which is 0.25, which is 0.75. So is not A, which is B and C, does that add up to 0.75? Yes, it does. Okay, example 4. 50 people went to a party, were surveyed. The results are shown in the table below. What is the probability that a randomly chosen person enjoys math? Okay, well, first we need to know, right, what's to get the probability that somebody enjoys math, it's the desired result over the possible results. So I need to know how many people liked math, 15, out of how many total people? We have to add up the 15 and the 35 to get the total people. And so that's 15 over 50, which is what? Let's go. Our calculator, 15 divided by 50 is 0.3, 0.30, or 30%. Okay, so 30% of the people there at the party liked math. 35% did not like math. Okay, what is the probability of flipping a coin and getting 3 heads in a row? Heads, head, head. Find the sample space when flipping a coin 3 times. Okay. So the sample space is going to be all the outcomes of flipping a coin 3 times. So the first flip, I could get heads or tails, right? That's the first flip. Okay. So the second flip, I could get either heads. So I could get heads, heads, or heads, tails, right? So I could get heads, heads, or heads, tails. Okay. Or I could get tails, heads, and tails, tails. Okay. Okay, what about the third flips? Okay, well, I kind of have to double these guys that I got, and I'm going to have to go heads, heads, tails, heads, heads, tails. Heads, tails, and tails, tails. Okay, so now I'm going to add my third flip. Okay, I could get heads, heads, heads. Okay. Okay, I could get heads, heads, tails. Okay. I could get heads, tails, heads, or heads, tails, tails. I could get tails, heads, heads, or tails, heads, tails, or tails, 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 or sorry, this should be heads, tails, tails, heads, or tails, tails, tails. Okay, so I can get all those possibilities. Okay, and so there are 8 possible outcomes here. Okay, so the probability of heads, 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 well, there's only one of those. Okay, there's only one of those out of the total 8 possibilities. 1 out of 8. Okay, so what's the probability of not getting 3 heads in a row? What's the probability of not getting, so the probability of not 3 heads is just going to be 1 minus the probability of getting 1 head. If I take 1 minus 1/8, I'll say this is 1 minus the probability of getting 3 heads. So 1 minus 1/8, that's going to be 7/8. What's the probability of flipping a coin 3 times and getting at least 1 tails? Probability of flipping a coin 3 times and getting at least 1 tails. So we want at least 1 tails. Well, the probability of at least 1 tails, okay, is equal to 1 minus the probability of no tails, of none, right? At least 1 is going to be that's the complement of probability of getting none of them, right? At least 1. So again, this is the exact same problem because the only one that doesn't have any tails, no tails, is that heads, heads, heads. So probability of getting at least 1 is 1 minus the probability of no tails, which is that 1/8. And so this is 7/8 again. Okay, so basically the same problem, just stated a little bit differently the second time. Okay, an event is unlikely if its probability is very small, such as 0.05 or less. An event is unusual, I should say if it is extremely high or low from what you would typically expect. Okay. We can find the probability of more than one event occurring by multiplying the probabilities. More on this later. What is the probability of flipping a coin twice and it landing on heads both times? Is this unusual? Okay, so the probability of flipping a coin twice and landing on heads is probability heads, heads. Okay, we could write out all the sample space, but we saw that writing out sample spaces can become very tedious at times. And so what we can do is we can say that this is just the probability of heads times the probability of heads. The probability of getting a heads out of one flip is 1 out of 2. There's 1 heads out of 2 sides. So this is 1/2 times 1/2. 1/2, which is 1/4, which is 0.25. Now, is that less than 0.05? No. So this is not unusual. Not unusual to get 2 heads in a row. Sorry about my writing here. Heads. Okay, it's not unusual to get 2 heads in a row. Okay. Okay, it is not less than. What's the probability of flipping a coin 10 times? Ooh. This is the probability, and 10 and it land on 10 times in a row. So this is a probability of 10 heads in a row. This is going to become 1/2 to the 10th power, okay, or 1/2 times 1/2 multiplied 10 times. Okay, this is equal to 1 over 1024. You can do that on a calculator. Okay, if we just kept multiplying 1/2 to the 10th power, or 1/2 times itself 10 times, you can see here, we get 1/2. Okay, and I'm going to raise that to the 10th power. Okay, is this number here. Okay, 0.000977. 0.000977. Is that less than 0.05? Yes. So this is an unusual result. Okay, this is an unusual result. Okay. Practice. When Mendel conducted his famous experiments with peas, one sample of offspring consisted of 428 green peas and 152 yellow peas. Based on those results, estimate the probability of getting an offspring pea that is green. Is the result reasonably close to the 3/4 as claimed by Mendel? Well, this tells me how many green peas and yellow peas, but this does not tell me how many total peas, right? So the probability of getting a green would be the 428 out of the total. Okay, 428. So I'd have to add these up. 428 plus 152. So 428 over, what's 428 plus 152? 428 plus 152 is 580. And I want to do 428 divided by 580 is 0.738, I would say, 0.738. So this is equal to 0.738. Okay, and is that close to 3/4? Well, 3/4 divided by 3 divided by 4, we would get 0.75. And so, yes, this is close. Yes, it is close. Okay, what we call this is the experimental result. And this is the theoretical result. And we'll see that the more trials that you do, the more and more trials. Here he did 580 trials, but the more and more trials you get, the closer the experimental will go to the theoretical. Okay. As n gets larger, the experimental will approach the theoretical. On their first date, Kelly asked Mike to guess the date of her birth, not including the year. what is the probability that Mike will guess correctly? Ignore leap years. So this is going to be 1 out of 365. Would it be likely for him to guess on the first try? Well, what is 1 over 365 as a decimal? 1 divided by 365. That's 0.0027. This is approximately 0.0027, which is less than 0.05. So it is not likely to guess on the first try. It is not likely to guess someone's birthday on the first try. If you were Kelly and Mike did guess correctly, would you believe his claim that he made a lucky guess? Or would you be convinced that he already knew when you were born? I would think Mike already knew, which would creep me out because it's the first date. Okay, already knew my birthday. He must have Googled me or something. My birthday. Okay, number 3. In a survey, 169 respondents say that they never use a credit card. 1227 say that they use it sometimes, and 2834 say that they use it frequently. What is the probability that a randomly selected person uses a credit card frequently? Okay. So again, we have to find out how many total people there are here. So 169 plus 1227 plus 2834, that's going to give me the total. Okay, 169 plus 1227 plus 2834 is 50. That's not right. What did I screwed up? It's 169 plus 1227 plus 2834. That's 4230, yes. So 4230 total people. Okay, and so we want to know what's the probability the random selected person uses a credit card frequently. So the frequently people were 2834. So this is 2834 over 4230. And we're going to say this is approximately what? 2834 divided by 4230 is about 0.67. So roughly 2/3. Okay, about 0.67 or 67% of the people use their credit card frequently. How are all these results affected by the fact that the responses were obtained by those who decided to respond to the survey posted on the internet? Okay, well, you could get a sampling bias. Okay. From the survey. Okay. Use the sample space listing the 8 samples, eight simple events that are possible when a couple has 3 children. You could get boy, 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 girl, boy, girl, boy. Okay, basically it's the same sample space as flipping a coin. Okay, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. Assuming that boys and girls are equally likely, so that 8 simple events are equally likely. Find the probability that when the couple has 3 children, there are exactly 2 girls. Okay, so which ones have exactly 2 girls here? 1, 2, 3, and it looks like that's it. Exactly 1, 2, 3, right? So we're going to say that's 3 out of 8 possible outcomes, 3 desired outcomes out of 8 possible outcomes. And that's going to be 3 divided by 8 is 0.375. If I move the decimal over twice, I get 37.5% of the time. The couple would end up with 2 girls. 2 girls. Okay. Okay, identify the sample space for the couple having 4 children. Ooh, that's a lot. Then find the probability of getting 3 girls and 1 boy. Okay, so for 4 children, right? So I'm going to start with the 3 children, and then I'm gonna double it. Okay, because like for the first one, I can get boy, 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 right? So if I have a boy, 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 what are the 2 outcomes here? Well, it's boy, 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 or boy, 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 girl. Okay, so I'll just use the one for the 3 space, and then I'll just double it. One will be a boy for the last one will be a girl for the last one. So this will be boy, boy, girl, and then a boy, and then a girl. Okay, boy, girl, boy, girl, boy, and then a boy, and then a girl. And then boy, girl, girl, boy, girl, girl, boy, girl, girl. And the last one will be a boy, and the last one will be a girl. This will be girl, boy, boy, girl, boy, boy. So last one boy, last one girl. And then we get girl, boy, girl, 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 boy, girl. Last one boy, last one girl. Girl, girl, boy, girl, girl, boy, girl, girl, boy. Last one boy, last one girl. And then finally girl, 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 girl. Last one boy, last one girl. And so 1, 2, 3, 4, 5, 6, 7, 8, 16 possible outcomes here. And then find the probability of getting 3 girls and 1 boy in any order. Okay, so 3 girls. We got 3 girls and 1 boy. Where's the other 3 girls? 3 girls and 1 boy. I got 3 girls and 1 boy here. Okay, any others? Yep, 1 right here. 3 girls and 1 boy. So that's 4 out of the 16, which is 1/4, which is 0.25, which is 25% of the time. Okay, suppose we roll a 6-sided die. Let events A and B defined as follows. Probability of rolling a number greater than or equal to 4, and the probability of rolling an odd number, okay? So we want to know what's the mathematical union for or, okay? What's the or statement mean here? Okay, probability A or B can occur. Okay, so let's draw a Venn diagram. Okay, what's the sample space? Okay, for our Venn diagram, the sample space is 1, 2, 3, 4, 5, or 6. That's the sample space. Okay, so our Venn diagram is going to look like this. Okay, a Venn diagram is just a diagram of circles that describes the interaction between 2 sets. Okay, so this is going to be set A, and this is going to be set B. Okay, or event A and event B. Okay, so what's the probability of rolling a number greater than 4? Okay, or what's the event of rolling a number greater than 4? Well, that's just 5 and 6, right? So the event of the greater than 4, oh, greater than or equal to 4, sorry, that's 4, 5, and 6. So that's 4, 4, 5, and 6, okay? What about event B, rolling an odd number? Well, that's 1, 3, and 5. Notice that 5 is in both categories. Okay, so I'm going to put the 5 in the middle here. Oops. Okay, I'm going to put the 5 in the middle, so showing that there's an overlap. It's hard to erase that. Okay, let me zoom in. erase U, there we go. And we're going to put the 5 in the middle. It shows that the 5 belongs to both set A, okay, or criteria A, and it belongs to set B. It's both bigger than 4, bigger than or equal to 4, greater than or equal to 4, and it's part, right? So this is the intersection. What we want is the union. The union, or the OR statement, is all possible outcomes. Possible outcomes in both event A or event B. Okay, so we could have 4, 5, and 6, right, as a possible outcome. Okay, but we also could have 1, 3, and 5 as outcomes. So what are all the possible numbers here? Well, it's 1, 3, 4, 5, and 6. That's the desired outcomes. Okay, that's the desired outcomes. Well, over how many possible outcomes? Well, it's 1, 2, 3, 4, 5, or 6. The only one that didn't get chosen was 2 because it's less than 4 and it's even. So this is going to be 5 outcomes over 6. Okay, so the probability of A or B is 5 out of 6. Okay, so we want everything inside here. Okay, we would shade everything inside. That's the union or the intersection. Okay, what's outside that? Well, 2. 2 would be outside. Okay, he's not a part of A or B. Okay, what about the probability of A and B? Okay, A and B. This means that they both have to occur. Both occur at the same time. Okay, this means that they both occur at the same time. It means that I have to have the probability that it's greater than or equal to 4, and it has to be odd. Okay, so it has to be greater than or equal to 4, and it has to be odd. Well, let's look at our Venn diagram again. Okay, so for event A, what is it? It's 1, it's 4, 5, or 6. For event B, it's 1, 3, or 5. And then 2 was on the outside. And so we want it when both of them occur. Both criteria have to be met for the and. It has to be, and there's only one value that works here, and that's 5. Okay, so the sample space or the event space that works is 5 over the sample space of 1, 2, 3, 4, 5, and 6. So there's 1 out of 6. Okay, the probability is 1/6. Okay, 20 children go to the park. 5 of them bring only a kite. 8 of them bring a bicycle. If 8 of the 8, 3 of them brought both a kite and a bicycle. Okay. Draw a Venn diagram to represent the situation. So we want to do our Venn diagram. Okay. So we're going to have kite and bike. So kite. Oops, draw a better circle than that. Kite and bike. Okay. So 20 children go. So there's a total of 20 kids. Okay. 8 of them bring 5 of them bring a kite only. So 5 of them only bring a kite. Okay. 8 of them bring a bicycle. Okay, so 8 total bring a bicycle. So think of it more like this, that 8 of them bring a bicycle. 8 of them bring a bicycle. But of those 8, 3 of them brought both a bike and a kite. Okay, so 3 of them are actually inside here. And so I have to subtract off 8 minus 3 to get 5 that only brought a bike. Okay, so oops. Okay, let me redraw this. Okay, be like this. Okay, but 5 of them only brought the bike. There we go. So that adds up to 13. Okay, 13, which means how many are outside that didn't bring a kite or a bike? Well, 20 minus 13 is 7. So 7 brought nothing. Okay, so 13 brought either a kite or a bike. Okay, and 7 brought nothing. Okay, what is the probability that chosen at random, that a child chosen at random brought both a kite and a bike? Well, who brought both kite and bike? Well, 3. So this is 3 out of 20. Okay. And if we go 3 divided by 20, we get 0.15. Okay, or 15%. So 15% brought a kite and a bicycle. Okay, who brought a kite or a bicycle? Oh, kite or a bicycle. Well, that's going to be the 5, the 3, and the 5. That's going to be 5 plus 3 plus 5, which is 13 over 20. Okay, which is going to be 13 over 20 is 0.65. Or 65%. Okay, so 65% brought a kite or a bicycle. Okay, you roll 2 dice and find the sum. List the sample space. Okay, so I'm not going to list all the sums. Like, well, I guess we could list all the sums. Okay, but you roll 2 dice and find the sum. Okay, so what would be the sum of 2 dice? What would be the probability that you would get, what would be the outcome of rolling 2 dice? Well, you could get a 2, you could get a 3, you could get a 4, you could get a 5, a 6, a 7, an 8, a 9, a 10, 11, or a 12. So that's the sample space for, okay. However, it's really not, because it depends on, of which one you roll first and which one you roll second. So this says that I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 outcomes. But those are just the sums. Okay, those are just the sums. Okay, but we don't know which combination of dice create all of those sums. Okay, so let's look at all the outcomes. Okay, so we have a 6x6 grid here for all the outcomes. Okay, so if I add 1 plus 1, I get 2. Okay. If I add 1 and 2, 3, 4, 5, 6, 7. Okay, if I do the next row, this is going to be 3, 4, 5, 6, 7, 8. If my first die is a 3, that's going to be 4, 5, 6, 7, 8, 9. If my first die is a 4, this is going to be 5, 6, 7, 8, 9, and 10. And if my first die is a 5, this is going to be 6, 7, 8, 9, 10, 11. And if my first die is a 6, paired up with all the other 6 die possible outcomes for the die, this is going to be 7, 8, 9, 10, 11, and 12. Okay. Okay, events A and B are disjoint, means that they're mutually exclusive, means that they can't occur at the same time. Okay, so you can't roll two die and have them come up, different, multiple times of 1 and 1. It's just, you roll 2 die, you get a roll. You roll another 2 die, you get another roll. They're independent of each other. They don't affect each other. Okay. 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 Here it says, what is the probability of rolling a 3 or a 4? So we need to get this chart to find the probability of rolling a 3 or a 4. So the probability of rolling a 3 or a 4, okay, is not 2 out of 11. Okay, it's not 2 out of 11. Don't make that mistake. Okay, it's not just 2. It's just not the number of sums out of the total number of sums. It's not 2 out of 11. Okay, it is this guy here, which is 1, 2, 3, 4, 5. This is 5 out of 36. Okay, because 6 by 6 grid, there's 36 outcomes here, and there's 5 that match that criteria. Okay. Okay, going back to disjoint, sorry about that. Okay, events A and B are disjoint, mutually exclusive. If they cannot occur at the same time, there is no overlap. So that just means that they can't happen at the same time. Okay, probability that somebody is pregnant, okay, 0.15, right? Probability that they're pregnant, 0.15. Probability that they're not pregnant, 0.85, okay? Okay, probability that you're male and you're pregnant, 0%. Okay, so you're either are or you're not. Okay, so either are or not. Okay, that means they're disjoint. Okay, either happens or it doesn't. Okay, randomly selecting someone who is registered Democrat. Examples that are disjoint. Okay, you're either registered Democrat or you're not. Well, you can't be registered as something else. Randomly selecting someone who's registered Republican. Okay, example of events that are not disjoint. Randomly selecting a student that is taking a statistics course. Okay, so taking a statistics course, randomly selecting a student taking a business course, could they be taking both at the same time? Yes. Okay, so those are not disjoint. Events that are disjoint. Flipping a coin once and it landing on heads. Flipping a coin once and it landing on tails. Okay. So that is disjoint. It either is heads or it's tails. Okay. Course grade, A, B, C, D, or F. Okay, that's disjoint. Okay, what is not disjoint? Rolling a die and getting an even number, rolling a die and getting a number greater than 3. Why is that not disjoint? Because the number 4 and 6, okay, satisfy both of them. That's the overlap. If there's overlap, it's not disjoint. Okay, or mutually exclusive. Okay, hobbies, tennis, swimming, blah, blah, blah. You can enjoy tennis and swimming. Can you enjoy swimming tennis? I don't know. Can you have a racket and play tennis? Probably not while you're swimming, but you can enjoy both. Okay, maybe not at the same time. Okay, complements, A and A complement are always disjoint. Okay, it always looks like this. If you're either in A or you're not in A, this would be A complement. Okay, you're either in A or you're not in A. Okay, so they're always disjoint. When two events A and B are disjoint, then the probability of their union, or sorry, probability of their intersection is 0. This is intersection. Remember, what was intersection? Intersection was the overlap, right? That was intersection. So when they're disjoint, the probability of the intersection is 0. Draw that a little bit nicer. Okay, so probability of the intersection. This is the intersection. Okay, so if they're disjoint, then what does that mean? That means that there is no intersection. Okay, there is no intersection. Probability of both of them happening is 0. Okay, no intersection. If disjoint. Okay, so there's no intersection if disjoint. Okay, and that's 3.1, 3.2. Okay, I will see you in the next video. Well, that'll take us for 3.3 to 3.5.